I've got to put it forward just in case. Just follow the exits, the green lights. The other thing is, could you please switch off your telephones? Because we still have a £50 fine, and we're desperate to find someone who's going to pay it this time. So please switch your telephones off, and we'll be okay there. Right, other than that, we have a few little things here, as you can see on the screen, who we are. We are the Royal Chartered Institute of the North of England, and that's the way we are. And we have quite a few things happening that we do, and this was actually something that we did last time we were on, which was the art of mining with microbes. It was very, very interesting. And here we are. Let's see where I'll go. Yes, and this is what we have coming up on the 29th of May, which isn't very far away. And this is going to be interesting too. It's amazing what you get actually here at the North of England Institute. You get some absolutely wonderful speakers, of which we have one here tonight. So again, on the 29th, don't miss it. Come along. Let's see what we have. And again, in June, 12th of June, we have Light Across the Water, the evolution of lighthouse technology. There we go. Right, here we are. You can see who we are. We're closely allied with the IOM3, the Institute of, Materials and what have you. I can never remember the order that they come in, so forgive me, IOM3. But there we are. You know, there's quite a lot here. What we have is we have lectures and conferences, which are here. We have an annual dinner, which I haven't seen for a year. Sorry? September. Oh, good. Right. Oh, well, that gives me time to save up enough for the ticket. Well, there we are. Yes. But there's a lot of other things going on here, you know, and as I say, the annual dinner, do field trips on occasions anyway, and the time will come when we do another one. So, you know, it's very, very interesting to be with the North of England Institute because there are benefits, mainly the post-nominals, for the young and up-and-coming and for the not-so-young and up-and-coming, to have a few letters after the names. We have, obviously, the guest lectures. There are discounts on the field trips and the annual dinner, which I've already mentioned. And please, yes, there are also opportunities to serve on our committees to shape the Institute for the future because, you know, I'm getting on in years. I'm probably past shaping for the future. Come on, let's tell the truth. So please, you younger ones who are, so let's say, under 65, please come along and try and help us out with a lot of these things. But we are developing and we are diversifying in a lot of the things that we do here at the Institute. So it's a very, very exciting time to be with the Institute. Let's put it that way. So here we are tonight. Anyway, rising the challenge of zero carbon aviation with Ian Kerr. Ian's worked as R&D manager for Honeywell Aerospace for the last 2 years, having previously worked across the aerospace, marine, rail and automotive industries in a variety of roles, most notably as R&D manager for Dido Metals Europe. For 10 years. My, that's a long time to be in a job, Ian. Sorry, I didn't want to make it sound bad. But yeah, he has a first degree in metallurgy and a Master of Science in mechanical engineering. Now, I could go on. Obviously, there's lots of other stuff I could say about Ian, but the best person to tell you about himself and about what he's putting forward tonight is Ian himself. So, Ian, welcome to the North of England Institute. And we look forward to hearing you.
Okay, well, thank you for the introduction. You hear me okay? Yep, cool. So, yeah, this talk tonight is, I appreciate aviation is not necessarily the heartbeat of the Northeast industrial scene. But it's a very, very important part of the UK economy from an industry perspective. And this is at a fairly high level. If you've got any questions, I believe policy is just to leave them to the end because that's easier to coordinate. But I'm more than happy to go into any greater detail on any of the things that I've got here at a higher level. Right, so really what I'm talk about is aircraft environmental controls. So what it is that we do here, particularly in Honeywell in the UK. Why we need to, as an industry in aviation, what are those things that are moving us towards decarbonisation, and what are the things that we're doing to get there, particularly what my group in the UK are participating in and leading in decarbonising certain aspects of where the aviation is. And then lastly, I'll touch on some of the things that are not necessarily as straightforward. It's not all about CO2, particularly in aviation. We've got other challenges that we're dealing with in order to decarbonise. And I'll touch on a few of those and explain some of the things that's happening, including a lot of it which is kind of UK is actually the heart of what is happening worldwide on some of these themes. So an aircraft ECS, how do you keep Joe Linton alive when he's in the air? Joe Linton flies back to Brazil. I may be out of date now, and he actually flew back last week. But when he flies back to Brazil, he's at about 40,000 feet, which is an Everest and a bit. He would freeze to death and asphyxiate in nothing flat, but for the fact that the aircraft has an environmental control system. So if I was giving this talk 90 years ago, the current state of the art for life support in terms of pilots, this is all UK technology developed in Yeovil in the site where I still work. And at that point, we developed an electrically heated flight suit. I wasn't involved in that at that time, but two Westland aeroplanes equipped with pressurized oxygen, electrically heated suits. They flew over the top of Mount Everest. And this is how it made to the London Illustrated News. I believe that although Wikipedia may be frowned upon for writing your presentations, the London Illustrated News being something of high repute, I believe these must be very, very good record of the first flight over Everest. What we don't have is any actual photographic evidence of that first flight. We do have a photographic record of the second flight over Everest. That's two Western Wallace aeroplanes equipped with technology coming out of Yeovil to fly at that altitude. The reason that there is a photograph of the second flight and not the first flight is we were only told to keep the pilot happy. Nobody said anything about keeping the camera happy. And on the first flight over Everest, they found that the camera froze solid, and there is absolutely no documentary evidence of it. Although if you see this one labeled some places as the first flight over Everest, let it pass, okay? During the next 90 years, things moved on at a pace. Really, what is now Honeywell Aerospace UK, at that point was the part of the Westland company down in the southwest. Westland weren't interested in this from the point of view of, oh, let's just fly over Mount Everest for the sake of it. Pretty much the same way as we didn't win the Shiner Trophy because we just were interested in flying fast. You know, it was the 30s, maybe not so dissimilar to today. There were civilian technologies being developed for use in wartime. And in wartime, Westland focused heavily into high altitude bombing. And the Westland Welking was one of the sort of, you know, world's first high altitude pardon me, bombers that was flying way above any flak. Come peacetime breaking out in 1946, Westland wanted to go in two different directions. High altitude was one part of the business. They decided to go into rotary wing aircraft with the other half of the business. The half that was high altitude was spun out into a company called Normal Air. And Normal Air then continued for the next, well, it continues to this day as Honeywell. It became Normal Air Garrett as part of the Garrett Turbocharger Group with Cliff Garrett's thing. That then was bought up by Allied Signal in the 90s. Allied Signal then morphed into Honeywell Aerospace as we are today. And if I was to give this talk in a year's time, Honeywell Aerospace is now morphing into something else as Honeywell has reached a size where it's going to divide under its own weight by some strange metastatus. But in that time, a lot of things developed in terms of the environmental control system. So with an aircraft, you have three groups of people fighting in different directions. The propulsion system and the aerodynamicist, they want to fly high. The drag is less. They have lots of things that they like to fly higher and higher. So those guys flying over Everest at 33K feet, we're now flying routinely at 40K feet at cruising altitude for an ambient condition. Airframers, structural engineers, I'll show you what a pressure vessel looks like later on, but you're not going to make one fly. The aircraft you're in when you head off to Mallorca or Joe Linton heads off to Sao Paulo is very, very leaky. So the only way that you're going to keep everybody happy inside that aircraft cabin is to constantly push air in. So typically this is bled from the compressor stage of the engine, hence the term bleed air. You can also, these days, electrically driven compressors are entering the market. Aviation is moving towards a more electrical, less mechanical footprint in terms of how we do things. If you go on a 787 Dreamliner, that is completely compressor driven. There's no mechanically takeoff on the engine for any of the air feed on a 787. But there's pros and cons to both. And touch a little bit more later on. In terms of this system, this has been around now since the early part of the jet age, okay? We came up with a solution, and in aviation, what we like to do with a solution when we have one is we like to rework it again and again and again and again. The reason being that to qualify an aircraft is billions of dollars, and to qualify one system on an aircraft is millions of dollars. Changing things costs a lot of money. There are enormous barriers to entry in aviation, and if we're not able to deal with those barriers effectively, then we end up with a very expensive product, and it's just not competitive. So in terms of conservative industries, we like to think of ourselves as being all modern and dynamic, but actually it is very, very conservative as how we go. So the bleed air system that would have existed on 747, planes of that ilk, on the early Airbus A300s through A320s into modern A330s, A380s, and whatever else is coming out now, really is based around the same system. Maybe some of the components change. The actual mechanics of how it works is robust and it's straightforward. So we take, add on, it's supposed to be this one, right. So we take air from the outside and we run it through a ram air duct, okay? So that is air that comes on a scoop. If you happen to look down and to your right as you board the aircraft, you may be able to see it just on the nacelle on some aircraft, just underneath the wing root. The bleed air coming from the aircraft, we will run it through a heat exchanger in this ram airflow. And because that bleed air is highly mechanically worked, it will be very hot, very energetic. Ram air is quite thin, but it's also very, very cold. So we get a big delta T, it's easy to cool. Simple thermodynamics, if you don't have a big delta T, then it's very, very hard to remove temperature. We then take that air and we run it through an air cycle machine. And an air cycle machine is essentially a turbocharger run backwards. So we take the energy from the bleed air on the outside, and we use that to compress it even further on the inlet. Because we've compressed it, it's now got the energy in it converted into high pressure, high temperature. We've got a big delta T again, so we can remove more energy because we've got that. and then we let it expand through the expander side, driving the compressor through the boost trap in the middle, and then we actually have a very, very efficient way of cooling air without relying on a refrigerant. The reason that we don't rely on a refrigerant, you've got a refrigerator sat at home in the kitchen, it's a very, very efficient system using a refrigerant. But if you use a refrigerant and it leaks, it goes from 100% performance to 0% performance. If you take an air cycle machine and you do some damage to it, you break a fin off or whatever, you may degrade the performance. You might need to actually do some work on it when you land, but there are no laybys in the sky. If your cooling system goes wrong, then you're going to flood that cabin with hot air, and that would not be pleasant for anybody who's in the cabin. We tend to rely on things that are robust performance, lightweight, and proven technology. Similarly, our heat exchangers in here, they tend to be plate fin type. Again, plate fin has been around for longer than I care to remember. It's robust, it's lightweight, and it's proven. There are a number of different options emerging now in terms of additive manufacturing, in terms of microtube, in terms of everything. You may have heard of a company called Reaction Engines, who were bankrupt, unfortunately, in Q4 last year. We were working heavily with Reaction Engines on a lot of things, and I've taken all that bit out of here because at the minute it's a bit up in the air as to what exactly happens to where we go with microtube, and I don't want to mislead you as to which way we're going. So in terms of what do Honeywell Aerospace actually do in Yeovil, that's us there surrounded by the red line. From our legacy, we're actually in the middle of what is now Leonardo. You can't access any of the doors that lead into our plant without walking through Leonardo's site. We're probably reasonably good neighbours, but good fences make good neighbours. But we've been sat there since the inception of the company in 1946. We will continue to be there. It's a good place. Yeovil is a very, very aerospace-oriented town. There's ourselves. There are Leonardo. It's where the British Army has its helicopter repair services. You've got the Fleet Air Arm just up the road at Yeovilton. You've got the Fleet Aero Museum in Yeovilton if you're ever in the area. There's a lot going on in the area. So we've got a lot of expertise in one particular industry. So these are the things that we make, and I'll try. So air management systems. So we make air conditioning, temperature controls. We do all of the pieces that we just described in the air cycle machines, but then we surround that into a system. And most of what we do is system-oriented. We don't do a lot of components. We tend to make all the interesting parts of an overall system. We can often work with the airframer in a way that says, right, we make the interesting bits, they make the things that are bits of tube. That works out to be more economic, but we'll still test that at a system level. So we will buy components from our customer in order to test everything that goes in the finished system. We will do bleed air systems, anti-ice systems for the wing, the leading edge of the wing. It's common to run some of this high temperature bleed air along there. You don't want ice forming on the leading edge of your wing. The easiest way to avoid that is to heat it locally. So we have anti-ice valve systems that will work. I mentioned earlier that the cabin itself is very leaky. We push in more air than would leak out through the existing leaks, if that makes sense. We then want to feed that air back out of the aircraft in a controlled fashion, because what you don't want is big surges in pressure. It's unpleasant enough when you come in to land at Newcastle and you feel your ears starting to pop. That's because your cabin altitude is going down from about 8,000 feet to ground level in Newcastle, which is pretty much sea level, to be honest. But you still want, during the flight portion, as you're coming over the UK and approaching that landing bay, you want the pressure to be constant. So the system is overpressurized, and then we feed that out. I don't know if anybody's involved in the diving industry, but essentially it is pretty much the same technology that you have on a diving regulator with a spring and a diaphragm that keeps that pressure constant in a cabin pressure control valve. We also have thrust recovery that's on there, and thrust recovery valves, we don't just push the air out of the airframe, we push it out backwards for obvious reasons. It costs energy to drive that system. When we're driving the system, we want to get as much of it back. And those are the fine margins that you're working with on all these systems, that every last bit of energy counts. Heat exchangers, we don't do here in the UK anymore. Those parts of our business were commoditized and sold off. We still do a lot of heat exchangers out in California and increasingly in places like Mexico. But we still use a lot of heat exchangers within Yeovil. So we work with the likes of, well, reaction engines as was our legacy supply chain, and also emerging AM manufacturers in the UK, companies like Hayata, Conflux, who we have built relationships with because we see them as integral parts of the systems that we build. Fuel tank inerting systems are essentially ways of generating nitrogen. As a plane, particularly as you come into land, you start to pull air into your fuel tank. If you do that, then you have potentially build-up of explosive atmosphere. There were occasions in the 70s when aeroplanes blew up because the fuel tank had an explosion. In order to avoid that, we have an inerting system. We take the oxygen out of the air, generally through pressure swing absorption or through a membrane system, and we make sure that the tank is pressurized with very, very low oxygen air, so it's not an explosive atmosphere. Interestingly, if we were talking 10 years ago, I'd say, well, okay, FTIS, fuel tank inerting systems, they're an old legacy system because the world was all moving towards hydrogen. As I'll explain later, hydrogen is still part of the mix, but sustainable aviation fuels mean that it's actually interesting to start thinking about what we can do with tank inerting systems again going forwards. Life support systems. So Yeovil's bread and butter has been military aviation from the get-go. We do a lot of dedicated life support systems on a lot of military platforms, F-35, Typhoon, etc. Those systems are dedicated to keeping one person alive under extreme circumstances. A military pilot can be breathing up to 95% pure oxygen at times. He doesn't carry all that with him. We have small-scale pressure swing absorption systems that generate oxygen demand in a modern aircraft. And the demand can be quite extreme. If you've ever been to Farnborough and you see somebody take off and then hit the afterburners and point their nose upwards, the ascents can be extreme if you're in a dogfight situation. So our equipment is designed to make sure that the pilot breathes something which is, trust me, not pleasant to breathe, but is still breathable, still going to keep him alive, going to keep him functioning, even under extreme circumstances. We also do anti-G. So it's not uncommon for a pilot, when you see them suited and booted, they have their flight trousers on, those trousers, when they pull a high G turn, will sense that there's a high G turn and inflate to push as much blood as possible back up to the brain so that it doesn't pass out. There's a lot of fine management goes on within there. Thermal management really is kind of where I spend most of my working day. So we have vapor cycle systems that are becoming more and more important. We have the air cycle systems, and also we have some liquid cooling systems, particularly where you've got avionics systems, be they military or civilian. All that electronics takes a lot of cooling, and it's not like running your laptop here where you can just blow it out with a fan. The amount of heat generated is high, and also it's often in very, very thin air. So the cooling you get from very thin air is very poor, so we have a lot of active cooling systems that are heavily integrated throughout the aircraft. And then finally, all that turbo knowledge that we have from running air cycles machines for the last 70 years, that's come out into lots of other areas like vac generators and fans, etc., all of which make important parts of the actual aircraft system. In order to do all of this engineering, in particular to qualify all of these components, then we have a first-class, world-class set of altitude chambers and other equipment. This big chamber you can see here is the biggest one we have on site. It was originally commissioned in the late 50s for the nose cone of Concorde. So if you kind of picture Concorde, you could fit the front chunk of Concorde into that chamber. At the minute, as you can see, we've got a mezzanine floor, and we tend to have one system assembling on the top half, one system being tested on the bottom half. So it's a very, very flexible facility. Not as unique as it was when it was built, but there are certainly no more than a dozen or so such facilities worldwide. We can fly that up to 51k feet, which is fairly high. Military applications can go substantially higher than that, but that's where we top out. We do have other chambers that would do slightly other applications. What is more, we can also link all of our altitude chambers together, and we can emulate what would happen to a pilot and the system that's keeping him alive at the point when he hits the ejection seat. So he hits the ejection seat, his cabin is going from whatever altitude it's managed at, typically sort of 20, 30,000 feet-ish sort of thing, to absolutely kind of like, you know, wherever he happens to be in the sky. So the decompression and the system that puts on, the stress that puts on our system is enormous. We want to make sure that as he ejects, he stays alive all the way down. And he may be ejecting at the top of climb for some reason. That system needs to keep him sustained until he's at ground level again. So everything has to work even through huge decompression swings. We do a lot of work on military, because it's our bread and butter. That's led to things on life support, where we've got a lot of knowledge and application areas, and we continue to generate new products leading to the 6th generation fighters that are now in development. But also we do a lot of ECS type stuff on environmental controls. Typically, as a company, we split our manufacturing. We do the smaller stuff here in the UK. We do the bigger stuff out in the US, just based on the size of production lines and the size of jigs and tooling we've got. But then we do the design work for both, dispersed between our Yeovils teams, our Torrance teams, and lots of other teams worldwide. You know, even when boiled down to just the aerospace components, then Honeywell Aerospace is a truly global company with a footprint in just about every market. No, wrong button. Right, so decarbonisation of aerospace, because it's only a few planes, right? It's not a big deal. There are far, far bigger priorities for things that need to reduce their carbon footprint. passenger numbers continue to grow. This is a prediction from the Waypoint report back in 2021. They took kind of a midpoint, high point, and a low point. Obviously, 2021, we were still recovering from COVID. We're much closer to that high point than even the midpoint as things are going. You know, people like to fly. Flying allows you to go for that business meeting in Berlin. Flying allows you to get to Malaga for a bit of sunshine. Flying allows you to go see the Rocky Mountains or Kilimanjaro or see your grandchildren on Australia or all those things. People like to fly. Particularly the growth in aviation in Asia as wealth, income increases among populations. More and more people can afford to fly, and they want to fly. You know, it gives you an awful lot of good things in your life, being able to get places. And as long as passenger numbers are going to continue to grow, it's beholding on us as an industry to reduce our carbon footprint. So this is a document from the ATI, which is the Aerospace Technology Institute. That's a UK charitable body that represents the UK industry overall. And ATI, if anybody's interested in getting into the aerospace industry and going, well, it's really daunting because I heard that there's all these problems with being part of the supply chain, qualifying my components, finding which tier ones and primes I can sell to, what the channels are, etc. ATI have made it their objective to make it as straightforward for UK SMEs and academia to work with the aviation industry. They have quite a lot of work going on to bring people in there and a lot of different activities aimed not just at the likes of me who already work in the industry, but a lot of other people to try and bring in new expertise, new knowledge, and keep building aerospace as part of the UK economy. That said, they've done this analysis, which is very, very small print on here, but there are a number of versions of this lasagna diagram. But the top line is always, this is how much carbon we would produce if we did nothing. The bottom line is always somewhere around about 0 in 2050. We know that the most conservative estimates of decarbonisation, governments want to reach net zero by 2050. Now, there's lots we can do. There's some things that we're going to offset. If you go onto your EasyJet booking form, you currently have the option to buy a tree and that will grow enough carbon to absorb for your flight. But there are other methods that we can do involving carbon capture and storage and other things that can offset the carbon created. And those measures are going to be there for the short term. There are a lot of work being done on sustainable aviation fuels, or SAF. Sustainable aviation fuel is a mixed bag. You can either say that, right, we will have a lot of it, or we go, well, actually, where are you going to find all the biomass to make sustainable aviation fuels from? Probably neither one of those. You know, the circumstances are not that cut and dried. There is a lot of certainty and a lot of uncertainty, but SAF will certainly be part of the picture. Hydrogen will be part of this. You know, for all of the decarbonisation of industry, hydrogen will play a part in different areas at different times. From an aviation perspective, then I don't think hydrogen will make it into very large aircraft very quickly, but there are lots of opportunities with smaller aircraft and other places that we can use it within the market. And that's gaining us a lot of experience as well. And then finally, there's a chunk around about flight operations. So a lot of the energy that we waste as an industry is very, very tied up with having the right aircraft at the right place at the right time. You know what it's like that you get to the airport and they say, no, we bumped you to the later flight because this one's not full. It's not a very optimized way, and it's a lot more expensive than a bus. So actually optimizing the way we run our flight operations is something that's quite key to where the industry will go. It's not something that in my group, because we're mainly mechanical engineers, that we work a lot on, but it is also something that's quite important from a perspective of where Honeywell plays into lots and lots of different things. My really inaccurate predictions are that we will have an ultra-efficient single-aisle aircraft by the mid-2030s. That will be an Airbus offering, most likely. You look at the players in the market, Airbus are probably going to lead, Boeing are probably going to follow. By mid-2050s, we should have functioning hydrogen-powered aircraft. A lot of things need to happen for that to happen, because it's not just about what you run the aircraft on. You need that fuel to be at the airport. You need to work on hydrogen generation, hydrogen storage, cryogenics, loads of fields. And there's lots of things we can do about flight planning. And those things will be ongoing and will be entering the market a lot sooner. It's a lot easier to change your flight operations planning and look at things that way than it is to actually invent a new aircraft. You know, new aircraft, $1 billion, tweaked to a computer program, cheaper. Not cheap, but cheaper. So what are we doing in the UK, within Honeywell, this is anyway? As well as the ATI, I mentioned earlier, there's also Clean Aviation. So the Clean Aviation Joint Undertaking is a European body funded by the Horizon Europe funding mechanism. They've been very good with us in terms of funding a couple of big projects that we're doing a lot of work on here in Yeovil. So what have we got? Well, we've got THEMA for HERA, thermal management for a hybrid electric regional aircraft. And that is something that we're running with Leonardo and also with Airbus. I've just concluded a project called ECLAIR, funded by the ATI. And there we looked at the bleed air quality and what we needed to do to improve the air quality coming into the cabin, but also what we could do to increase the efficiency of the bleed air system overall. A lot of the things that we started in ECLAIR are now continuing through THEMA. Where they'll go next is into a consortium called Strata. We believe that it's the time that additive manufacturing can take its stage. It's currently been difficult to get AM components to fly an aircraft. A recent ATI survey concluded there were probably less than a dozen AM components functionally that were flying in aircraft systems, because it's very difficult to replace what's already there, because you've got to certify it, qualify it, etc. The hybrid electric regional aircraft, we still provide some inputs to that. That is a project that Leonardo went. That really is becoming kind of a paper exercise, so that's dying down. But there's also a 1 megawatt fuel cell system that we're developing, mainly colleagues in the Czech Republic. We do some work, bring some of our expertise from our supply chain, particularly around the thermal management and other things. Newborn's quite an exciting project, looking at a pipistrel aircraft. And all of this takes a lot of partners. I'm not going to go through all of these people, but we work with a lot of different people from across UK and Europe in order to make these things happen. As a company, Honeywell are committed to our environmental goals. So we very much put our R&D spend in those sort of areas. So the Horizon Europe ones, THEMA, as you can see, sort of big partnerships. But just to stress the sort of, international nature of these things, Honeywell, we're here in the UK, but my team also has people in Poland, in Germany, in France, in Czech Republic. Airbus are in Toulouse, Hamburg, Bristol. Fraunhofer are German, Leonardo, that's in Italy, not in the UK. Reaction engines were UK, but sadly no longer here. Collins, the tech center is in Cork in Ireland. Nord Micro, they're German. Liebherr, mainly in France and Toulouse, and so on. So there's a very, very multinational, multi-company flavor to all these things. Newborn with the large fuel cell, you know, mainly that is focused upon what Pipistrel are doing as an organization. Their 19-seater aircraft is a good entry point for that. And then, as I said, the paper exercise around sort of the HERA project. So the newborn system, this is quite an old diagram. It's evolved a lot since this diagram was put out. But it is the whole integrated system. It will be a ground demo. It will be on an airfield in Slovakia in the early part of next year, that we will fire up the fuel cell portion of this, and we'll have all of the ancillary equipment around it in order to actually operate it as it would do packaged into an airframe. There are people in the UK, Zero Avia, Project Fresson, who are trying to fly hydrogen aircraft. Our view is that there's a lot of things that need to happen before we want to actually fly things using hydrogen. As I say, it's quite a long way out. Airbus pushed their roadmap out by 10 years earlier on, about February of this year. There's been quite a lot of restructuring around, right? We can't let best get in the way of better. We need the ultra-efficient aircraft first. That will help us decarbonise. That will use a lot of UK technology from Airbus, from ourselves, and that will then bring down emissions substantially. But then hydrogen needs to follow on. So it's not either or, it's a complicated mix of which ones are possible and how quickly they can be brought to be robust engineering systems. Thema for HERA is where I spend most of my working days. We're working on three things. We're working on an advanced bleed system. At the core of that is a very, very complicated jet pumping arrangement, so we can reduce the energy that's being dragged from the jet engine. The jet engine uses a mixture of HP and LP bleed, low pressure, not as worked, but if you don't have the high pressure in there, so we often use a Venturi type arrangement or jet pump in order to do it. But that tends to be optimized for one phase of flight and a bit rubbish for the rest of flight. We are actually optimizing how we can make it into a multi-position jet pump, so it will be optimized at different phases of flight in a different way. It's technically very demanding, and we do a lot of CFD again and again and again, but we're getting there. We can actuate that system now, and it should be sort of mature to TRL6 in time for the next gen single aisle aircraft. Flow sensors, we do a lot of things in aerospace are done because they're regulated. You must supply a certain amount of air to an aircraft cabin. If your flow sensor has an accuracy of plus or minus 5%, then you're going to have to supply 105% to guarantee that you're always at the 100% required. So actually just making systems more accurate, we found brings big savings in terms of the overall operation. Vapor cycle system. I mentioned earlier, the vapor cycle system works as your fridge does in pretty much every regard, but it's not been favorable within aerospace. The modern refrigerants that are being developed by Honeywell again, not in the UK, but in the US, the Solstice range of refrigerants operate at much lower pressures. Making a leak-resistant system using something like Solstice is a lot more practical option. So we're looking again at vapor cycle systems and how they come into the mix and how that works. And then it's not just at the actual point when we're doing the cooling, but it's also the cabin air compression and everything else that goes on around that. A lot of complicated options that we're trying to trade, but we've got to work all the technologies because for different applications, They're all eventually going to be needed. It's not just CO2. Everybody likes to think of, right, carbon emissions are carbon emissions. The fact is, in the UK, we're at the forefront of the non-CO2 emission mitigation. Contrails, a lot of work that came out of David Lee's group at Manchester Met a few years back showed that actually contrails contribute to global warming. They form high altitude cirrus clouds. The cirrus clouds reflect stuff back to Earth, as per this nice diagram, again, courtesy of the ATI. The interaction between the aircraft, the emissions coming out of the tailpipe, ice crystals that are supersaturated in certain areas of the sky form contrails, and they form persistent clouds that reflect heat back downwards. I don't pretend to understand the physics of all of that. It's a very complicated and emerging area, but we're working with people within that area because we see it as an opportunity to improve what we do as a business, improve what we do in terms of our carbon footprint. Some of the estimates, 50% of global warming impact of aviation could be from cirrus cloud formation. There's a lot of acronyms. The ISSRs and the UTLS are things that I must admit, when we started this journey a couple of years ago in a discussion with ATI, where they said there's a need for something like this, I have no idea what you're talking about, and I've been doing aerospace for a long time, and I don't even know what these acronyms are. But there are a lot of interesting work to be done here in the UK on contrails. It's an area where we've got world-class science happening, and it's an area where we want to lean into that. A lot of the policies that I'm looking at is, can you detect, can you predict, can you avoid? If you avoid making a contrail, you reduce your carbon footprint as an aircraft. We are looking very much at the detect side of this. This is our, we've done a lot of work on sensors, measurement, etc. here in Yeovil, and we are therefore, we think that we know what we want to do. We think we know how we have to do it. We're just not altogether clear on how we get that and assemble all the pieces. We're working with ATI now to see how we work on that. Currently, for moisture detection, there's no available viable technology. You can go with something very expensive, but you're not going to get Lufthansa to fit an A320 with $100,000 worth of mass spectrometer. There's lots of things that we could do, and we are working with our academic and industry partners. Unfortunately, I'm pretty sure that our patent for how we were going to do this was filed a week ago, but I haven't heard from the lawyers this morning, so that bit's blank for the time being. Oh, and I was thinking that I hadn't put down what the UTLS was, the upper troposphere, lower stratosphere, and ice supersaturated regions. So, in conclusion, why is the picture of the drone? Because I start with a picture of a drone, mainly because when I was asked to write an abstract for this, I was stood next to the drone and I thought, oh, here's a picture to stick on the abstract. But we bought that drone last year. We're looking at it as just a test bed for emerging technologies. Some of those are in my domain, mechanical engineering, etc. A lot of those technologies are things like SATCOMs, etc. So although we don't have, wrong button, it happening in Yeovil, in Tewkesbury we make the VersaWave, which is a small footprint, low power SATCOM device. If you want to fly your drone over the horizon, in drone terms BV loss, then it's an ideal device. We also are developing in the US, and more latterly probably going to do a bit more work on this in the UK, a small fuel cell. Fuel cells make a lot of sense for drones in certain applications. There are people in the world who don't want to go, oh, it's cold outside, my drone won't work. I'll let you work out which sort of people those are that go and do sorties in the Arctic or maybe in the desert. They want something that works wherever they are operating. So we have a small drone with a drop-in capability. We're engineering that to be a replacement for a battery pack on existing drones. We will be partnering with UK drone makers to say, right, we can just offer this as an alternative. Don't put a battery pack, same footprint, put in a fuel tank and a Honeywell fuel cell, and that will provide you a more robust power solution. So, lots of things going on. I think that was probably 40 minutes, but I ran out of clock, so hopefully I haven't gone on for too long. But thank you for your time, and appreciate it.
Wow, Ian. Yes, you've, I think your first statement there, right at the very beginning, showing us flying over Everest, shows you how quickly we develop things in the world now, don't we?
Yep.
And not only did we do it quickly then, but it's advancing at such a rate now. And, you know, you wonder, where are we going to end with all of this? You know, yes, you said people love to fly, and we do need to fly because communication's so important in family and business and what have you. And the extent we've got to go to get to this is quite incredible. You know, I mean, you've told us about so many different systems and aircraft there, and that's just to get the thing off the ground, you know. And it's amazing how big aircraft are now. It's amazing. But anyway, Chris, we obviously have an answer and question session.
Hi, David Granger from Sunderland. Very interesting, Ian. I mean, it's a fascinating topic. I want to ask you about sustainable aviation fuel. A couple of months ago, I think, there was media reports about a company building a factory in Sunderland, in the port, using old tyres to produce sustainable aviation fuel. There's talk about 1 million tyres a year or something like that. Do you know anything about this, or what's your view on this sort of technology?
So I'm not so familiar with what's happening in Sunderland, as you may have noticed from Joe Linton, but certainly the key parts for sustainable aviation fuel to work, you need a feedstock which is consistent. You know, you're going to run it through a refinery process. We're very skilled at what we do in terms of refining crudes, etc., and we know what is in the different crudes from different parts of the world. Refineries are built to deal with a very, very uniform feedstock. Also, if we're going to use biomass, you know, mustard seeds and things like that have been used. They're clearly not long-term solutions because the world has an increasing population and only so much farmland. So things like using old tyres to do it, I would imagine was a very good idea. Now, whether it would make the volumes is, I don't know how many old tyres there are and how much fuel you would get from one old tyre, but it certainly sounds like a viable sort of approach when it comes to sustainable aviation fuel.
I seem to remember that about 20 million tyres are, you know, in effect, finished with each year in the UK, and you know, hundreds of millions worldwide. So I suppose there is a supply chain for the fuel if it works properly. Thank you.
Thank you. Great talk, Ian. Richard Bernard, I'm an engineering consultant. You mentioned qualification a couple of times. It's interesting, isn't it? Different industries in the world have evolved their own way. Aircraft different from rail, different from nuclear. But aircraft, I think, is probably unique, where the regulator allows this approach to qualification, where when you make a change, especially to a critical component, the aircraft industry is allowed to basically just qualify the change. In every other industry that I know where it's a critical component, you've got to go back to basics, even for quite a small change. I'm wondering how many changes you will make to a particular component or a system before you decide, you know what, we've made a lot of changes there, we're going to go back to the, because certainly the aircraft industry is being caught out with that. Having the 737 is a good example, I guess, where they, you know.
Yeah, I prefer not to comment on one of Honeywell's biggest customers, but yes, there have been some incidents where you think that isn't the industry that I'm familiar with. That said, clearly a lot of the problems that, say, the Air Alaska situation with bolts not being done up, those are quality control incidents. They're nothing to do with it. If the bolts were there, the aircraft would work. Now, the manufacturing process is typically robust, and certainly AS9100 standards are as rigorous as any of the other quality standards that, you know, you could probably get away with slightly more latitude in automotive industries on TS 6949 than you can do with AS9100. But I mean, a lot of qualification is based on similarity, and we tend not to deviate very much from what we're familiar with. That's one thing that makes it quite exciting now, is that if you're moving from a system that is based on, say, a conventional air cycle machine and a very, very dumb bleed system with a fixed jet pump that is using a plate fin heat exchanger, and then you're saying, well, actually, I like the reaction engine microtube heat exchanger. It happens to fit in quite nicely. And I'm losing space because Rolls-Royce's ultra-high bypass ratio engine is going to be enormous. So I'm trying to fit components into a smaller space. This is very appealing. I need to do all these things. We're changing an awful lot of things at once. We know what we're doing when it comes to the qualification, and I'm confident that we can get it right as an industry. Whether or not we can do it to the price point that everybody's going to demand in the timescales that are going to be demanded. I said there that my very inaccurate estimate was mid-2030s for the next gen single aisle. I don't think the problems will be so much in the technology development. The problems are going to be that period beyond first flight, as lots of things in that ecosystem are shored up, and we've done a lot of changes, and we're no different to any other industry in terms of, if you look around the room, there's an awful lot of grey hair in here. We do need young people coming into the industry. We do need to keep training people up. We have a lot of apprentices. We have an enormous apprentice program because we see the value in training people up now, because in 5-10 years' time, we're going to need a lot more people. There's going to be so much more engineering test activity going on.
That's great, thank you.
Anyone else? Yes?
Yes? Keith Hutchinson, North of England Institute. Fantastic talk, Ian. Thank you very much. I know I bent your arm to come up and do it. So thank you for coming up all the way from the southwest. I was standing where you were, I think about 3 years ago, giving a talk about slightly bigger, slower things, and that being ships. Talking about how to increase efficiency of the hull forms and the propulsion systems and the fuels, and what options were for the fuels. Shipping is under big pressure. Its production rate is about 2.5% of the global CO2 emissions. And I know you haven't,
Yep.
I know I just talked about CO2, but if we can talk about CO2, cement I think is about 7. What is aircraft? And given what aircraft is, shipping now has, just about a month ago, had a big shake-up in that they've actually put a price on carbon through the International Maritime Organization. What pressures are being put on the aircraft industry to actually decarbonise? Thank you.
So there's an organisation called IATA, who are an industry umbrella. They've set certain targets in terms of where the industry wants to go. Pre-COVID, there was some quite clear movement through the Kerr initiative with all of the industry players involved in setting targets to decarbonise completely by 2050, as you can see from the chart from ATI. Post-COVID, the aircraft industry was probably more affected than just about anybody else in 2020, 21, 22. Passenger numbers decreased drastically. I think we're still struggling with the balance between investing for the future and investing to rebuild a business. And you know, that's not a Honeywell thing, that's an aviation industry worldwide. But the targets are to get to zero by 2050. A lot of that is going to be offsetting. Now, in terms of the major players, Airbus have got their own targets. If you go onto the Boeing website and look for their Cascade tool, they allow you to, in real time, put your own assumptions in. I think that so this will happen. I think there will be this much aviation fuel available. I think that somebody will have a breakthrough in batteries. I think that somebody's going to fix hydrogen fuel cells and fuel tankerage, etc. And if all those happen, what does that mean in terms of what the outcomes for the industry are? And Boeing made that available to everybody. You could just go onto Cascades and mess around, draw yourself some nice, pretty coloured graphs. But one of the things they allow you to do is, right, well, what do you think is going to be left over at the end? What is your target? How hard are you going to make it on yourself to achieve that net zero by 2050? But that remains our target as an industry. As I said, there are serious headwinds and also a lot of uncertainty about how we get there, but that remains the target.
And just to give an idea of the emissions, what percentage of emissions, of the global emissions, does come from aircraft?
Something around about 1%.
Thank you.
Thank you very much. It's a fascinating talk. Genevieve Warwick, I'm a university-based art historian. I'm here currently to work in the library with a question about sculpture and sculptural materials, which of course are all mined, and the metallurgy behind that. I was, of course, delighted to see Leonardo's name still carries in the aviation industry, and in a professional capacity, what I know about aviation is limited to Leonardo only 400 years ago. So, in my work, I travel constantly. I fly all the time to visit galleries and museums around the world, and I feel guilty about my carbon footprint in that regard, and it's very encouraging to know that this is being addressed and that there are solutions in sight. I very much appreciate that the solutions need to be safe and that they need to be cost-effective. One of the things about flying and the budget airlines that we all use is that it means that people can fly all over the world for very little money, and it actually plays an important role in education, in democratizing access to culture. In terms of citizenship, it plays its part in forging tolerance through exposure and contact with other cultures and ways of thinking and ways of doing things. So we can think of aviation as between holiday and work, but I think it also plays a part in education, which is an interesting one to reflect on. My question is a very, very simple one, possibly a simpleton one. Does it make any difference if you adjust the temperature as an interim solution, if you adjust the temperature in flight cabins? I'm thinking, of course, of air conditioning, of course, famously having been a big problem. And one of the solutions in North American culture over the last 40 years has been to reduce temperatures of heating during the winter and reduce temperatures of air conditioning in the summer. So is there any mileage for aviation in simply bringing the cabin temperature, reducing the amount of cool air that's going into the cabin?
Okay, so one of the things I mentioned there was that we'd been doing work on a previous project, eClear, on air quality within the aircraft cabin. That was actually the successor to another project called UK, and part of the work that we did there was underneath the mountainside in Germany, just north of Munich, there is half of an A310 cabin, fully instrumented, and they can fly that aircraft. So we took a cohort of, I forget how many, but about 30 at a time passengers, and we did different things to the environment on the flight to see what were the tolerances. We worked with the Munich University Hospital we did a lot of psychological analysis, and they had batteries of tests of these things you can go on the internet and find out your IQ and whatever else things. And they did all this testing, and we have mapped where we think you can push the aircraft cabin to. From the point of view of you as an individual traveller, that's not going to make any difference until we change the system, and we can't change the system until the next generation of aircraft come along. So we know what can be done. We know when it starts to have an impact. You know, and the last thing you want is you start changing the environment. It's not just you as a passenger. There's somebody pushing a trolley up and down, serving you drinks, running around, doing all those things that you need to do. They need to be with it. You know, those flight crew need to be taken care of because they fly more miles than any of us. So we do take sort of quite seriously what is happening to all those people in the industry. But certainly there are things that we can do systemically as we go into the next generation, where we look at, right, what is achievable, what is realistic. So again, it's not the answer you want, because it would be nice to think, oh, I just turned down that air vent and saved the world, but it is coming along.
Well, thank you. I wish you well with this research, and it's great to hear that there is a solution that will emerge. We'll take that forward. Thank you.
All right, thank you.
Do we have any more?
David Bell, Newcastle. Back in the days of smoking on planes, they had to have far more kind of changes of air to keep the quality acceptable. And so the great advantage of banning smoking was the fact that they could do less circulations, which made things more efficient. But the downside was that it made it very much more difficult to spot cracks in the structure. When you strip off the paint, you could see the black stains where the nicotine had come through the crack. What sort of monitoring could be put in place to actually kind of spot these sort of long-term stress-orientated changes? Because remember in the Comet, it was not realized that square windows would cause a problem. So are they Honeywell looking at sort of monitoring of that sort of area?
That is more of an aerostructures problem. I can tell you what the industry is doing. You mentioned square windows. Why have a window? To be honest, it's the most boring bit of an aeroplane, and mainly you put a blind down. So one intervention that people are working on that I've seen is to have TV screens instead of windows. It actually brings quite a lot of saving in terms of weight. Seems dumb to me, but we live in a world where more screens is less weight. Another thing that has been done is, can you build sensors into aircraft? So real-time monitoring of what is happening with the airframe. And you know, we're looking to put in sensors because we want to monitor what we're flying through, but also those sensors can be inward-facing and look at what is happening to the airframe in real time. And instead of going, right, we're now going to look at the stress strain curve, do Miner's equation and all those things, you can actually generate much more data. Where it has changed from our perspective in terms of our repair and overhaul operation is on a cabin pressure control system, part of the repair operation was to take a hammer and chisel to the big black goopy mess that gathered around the cabin outflow. So the standard mode of failure for all cabin pressure control systems until they stopped smoking on aircraft was that it eventually choked up under the weight of nicotine. There would just be a big black congealed lump on top of that valve as all of that smoke eventually made its way out. So it's not just coming out through the airframe, it actually causes quite a big problem on the cabin pressure control system.
Thank you.
Right, well, I think we'll reach a point there. That absolutely wonderful talk. You know, it's mind-boggling the amount of stuff you've got to do and what to work on to make these things even just a slight bit more efficient. But anyway, I'd like to call on David Granger to give a vote of thanks because obviously we've all enjoyed it this evening.
Now it's past president, we'll call you at the moment, is it right? Yeah. Members, ladies and gentlemen, visitors, thank you, Ian. That was a very interesting talk. I'm not going to praise it because it's too much, but I like the first picture you showed of the Everest, as Steve said, how things have changed. 10 years ago, I think I was actually in Nepal and did, the tourist flight to look at Everest. We didn't get up as high as Everest, obviously, and that was in a pressurized plane, so it wasn't a problem. But you can appreciate, was it 1932, was it 33?
33, yeah.
33, well, not all that long ago, really, how things have changed. So that's one aspect of the aviation industry. From a more parochial aspect, it's very interesting to see what Honeywell is doing, Honeywell UK is doing in terms of decarbonisation, all the very, very interesting technological advances you're doing down in the southwest. Very, very interesting. And I'm very interested in this idea of the research into the contrails. I mean, my wife has a thing about contrails. You see, sitting in the garden on a nice sunny morning, and you see the contrails coming across, and 2 hours later, there's a haze over most of the sky. If will be able to get rid of these contrails, as I say, it'll make a big impression on the global warming effect of aviation. So, well, it's not a small thing, but it's a very interesting aspect of this decarbonisation and just the change in climate. So, I mean, things like that. I never thought of it actually. The research is going into aspects of that. So, very, very interesting. Thank you for your time. I found it a fascinating talk, and thank you once again. And could you please show our appreciation? Thank you very much.
Wonderful, Ian. Thank you very much
Thank
indeed.
you. Thanks for hosting.
Well, wonderful. So we'll go through a few of the little things that we do to close down here on a lecture evening. I've told you about what was coming up within the next months. I think, yes, we've got this one coming on the 29th, which should be very interesting. And let's see, have we got anything coming up? Just that's it. Lovely, yes. Another one, Light Across the Water, the evolution of the lighthouse and the technology. Honestly, you can't afford to miss this one because it saved so many lives having lighthouses around, not just our coast, but every coast in the world. So that's another one that's really, really worth watching. So I'll conclude with just saying a few closing remarks. And thanks very much again, Ian, for taking the trouble to come so far to give us this very interesting talk, and we do appreciate that. So the last lines are, can you please remember to sign your names in the book and the sheet? It's very important to us to have that. And there are, a few associations we have with the IOM3, as I say. And please remember, if you're a member of any other institutions and you're interested in IOM3, please get in touch. It's on the, the internet, very, very open, so you can do that. But more so, I'm going to say, if you enjoy what you've seen here this evening and you know what's coming along, think about coming along to a few more of the lectures. And after you've come along to a few more of them, you might just be tempted to take up membership with us, because obviously, like all associations and institutions, we desperately need members. So please take that. So thank you very much for your attendance this evening. It's been absolutely wonderful to see you all, and I hope I see you on the 29th, isn't it? 29th? Lovely. See you all on the 29th. Bring your friends. Thank you very much indeed.